So it's the weekend and you're finally doing your math homework. Hopefully it's more Friday or Saturday than Sunday night, but hey, you never know. Thank you for coming. This is Chapter 5, Section 4. We're talking about complex numbers and imaginary numbers. We are on Course Pack page 514 and 515. These notes are in the book so you can follow along in the Course Pack. So this is Course Pack page 514 and 515. Before we start in the Course Pack, I want to talk about where this idea that we're going to talk about comes from. And what it is let's say I gave you this problem. We just did a quiz over this on Friday. To solve for the x squared, I subtract 10 from both sides. You get 3x squared is equal to negative 36. Divide both sides. There it goes. Divide both sides by 3 to get x squared by itself. And now I take a square root of both sides. And I get x is equal to plus or minus the square root of negative 12. Up to this point, every time we've seen a problem like this, we've said, no, you can't have the square root of a negative number. You can only have square roots of a positive number. The question is, however, what if I did take a square root of a negative number? What would it look like? What would it be? That's what complex and imaginary numbers are about. That's what we're going to talk about. So let's start in our course pack. Solve x squared equals negative 1. This equation has no real number solutions because the square of any real number x is never negative. Anytime I square something, 5 times 5 is positive 25. Negative 7 times negative 7 is positive 49. Realize the square of a number is never negative. However, to overcome this problem, mathematicians created an expanded number system, or a system of numbers, using the imaginary unit I, defined as I equals the square root of negative 1. It's weird, it's odd, it stands for imaginary, but the idea is, what if I could have a square root of a negative number? What would it look like? And we're using the letter I to stand for that. Note that I squared is equal to negative 1. The imaginary unit I can be used to write the square root of any negative number. So imaginary numbers, there is no life I know to compare with the pure imagination. Living there, you'll be free if you truly wish to be. Love, Willy Wonka. A complex number is written in standard form as a number a plus bi, where a and b are real numbers. The number a is the real part of the complex number, and the number bi is the imaginary part. If b does not equal 0, then a plus bi is called an imaginary number. Example, 2 plus 3i. If a equals 0 and b does not equal 0, then a plus bi is a pure imaginary number, meaning 6i. What in the world does this look like? What does this mean? Adding and subtracting complex numbers. Write the expression as a complex number in standard form, a plus bi. Just like things we've done in the past, I'm adding, so all I want to do is add like terms. This is 4 plus 3 and plus negative I plus 2i. 4 plus 3 is 7. Negative I plus 2i is positive I. All I'm doing here is combining like terms. 7 plus I is my final answer. It's in standard form because I have my real part first and my imaginary part second. Let's try letter B. Letter B, again, when I combine like terms, this is 7 minus 1, funky one, 7 minus 1, plus a negative 5i minus a negative 5i, so that's plus 5i. 7 minus 1 is 6. Negative I, negative 5i, positive 5i cancel, so I just end up with the real part, 6. That's my number, and it's a real number. Let's try letter C. Again, what I'm going to do is I'm going to make things a little easier on myself, and I'm going to distribute the negative into the parenthesis. So it's 6 plus 2 minus 9i minus 8 plus 4i. Combine like terms, I'm going to combine the 6, the 2, and the negative 8. 6 plus 2 is 8, minus 8 is 0. Negative 9i plus 4i is negative, let's try that again. Negative 5i. Realize this is just a pure imaginary number with no real part. So that is my answer. That's combining like terms, adding and subtracting imaginary numbers. What happens if I multiply complex numbers? To multiply two complex numbers, use the distributive property or the FOIL method, just as you do when multiplying real numbers or algebraic expressions. Example 2, write the expression as a complex number in standard form. A plus bi. Remember, a is the real part, bi is the imaginary part. And we need to remember that I squared is negative 1. We'll see how that works in just 1 second. So I want to distribute 5i into my parentheses. 5i times a negative 2 is negative 10. I love my smartboard. 5i times negative 2 is negative 10i. 5i times I is positive 5i squared. The I squared, we use our identity that I squared is equal to negative 1. So I'm going to rewrite this as negative 10i minus 5. It is now the real part of this. So to put it in standard form, I end up with negative 5 minus 10i. That's the weird, funky part. I squared is negative 1, so I squared becomes this negative in this problem over here, so I get negative 5 minus 10i as my final answer. Let's do a couple more like this to see what else this can do. Again, I want to FOIL first. 7 times negative 1 is negative 7. Outer, 7 times 2i is 14i. Inner, negative 4i times a negative 1 is positive 4i. And last, negative 4i times 2i is negative 8i squared. Combine like terms here. I get negative 7 plus 18i. This I squared, again, changes into a negative 1, so this becomes plus 8. Now I need to combine like terms of negative 7 and plus 8, so I get 1 plus 18i. My answer should always have, at most, a real term and an imaginary term. There shouldn't be any other terms. The I squared becomes negative 1, and I get negative 1 times negative 1 gives me positive 8, and the I squared goes away. Combine like terms, I get 1 plus 18i. Letter C is going to be something that is very useful, if my board will actually work. There we go. These are called conjugates, even to the point they are called complex conjugates. They're complex conjugates because the real terms are the same, the imaginary terms are the same, and the only difference is one is positive and one is negative. Let's see what happens when I multiply complex conjugates. For FOIL, first, 6 times 6 is 36. Outer, 6 times negative 3i is negative 18i. Inner, 3i times 6 is positive 18i. And last, 3i times a negative 3i is negative 9i squared. Again, when I come back through here, 36 stays the way it is. Negative 18i plus 18i cancels out. The I squared becomes a negative 1 times a negative 9 becomes a positive 9. So 36 plus 9, my final answer is 45. 5. I multiplied two complex numbers, and I came up with a real number. That's huge. That's what a complex conjugate does for me. I'm able to multiply two complex numbers and come up with only the real part. It's a neat thing, and again, it's all because the I squared times I gives me the positive 9, and the middle terms cancel out. Let's talk about this conjugate thing in the next part. Dividing complex numbers. In part C of example 2, on the previous page, notice that the two factors 6 plus 3i and 6 minus 3i have the same form, a plus bi and a minus bi. Such numbers, as I said, are called complex conjugates. The product of complex conjugates is always a real number. Therefore, you can use complex conjugates to write the quotient of two complex numbers in standard form. So let's try this. Example 3. Write the quotient 5 plus 3i divided by 1 plus 2i as a complex number in standard form. Remember that I squared is equal to negative 1. Let's see what this does for us. 5 plus 3i divided by 1 minus 2. Let's try that again. 5 plus 3i divided by 1 minus 2i. I want to get rid of my denominator. I don't want to divide by this complex number. So I want to multiply by my complex conjugate, 1 plus 2i. Just the complex conjugate of the denominator, but I need to do it in both parts. So I put parentheses on these two parts because I know I'll multiply. So in the top, I'm going to FOIL. 5 times 1, let's put this down here. 5 times 1 is 5, that's first. Outer, 5 times 2i is 10i. Inner, 3i times 1 is 3i. Last, 3i times 2i is positive 6i squared. That's my numerator. My denominator, 1 times 1 is 1. That's my first. My outer is positive 2i. My inner is negative 2i. And my last is negative 2i squared. If I simplify, too low, that'll work. In my numerator, the 6i squared becomes negative 6 plus 5 is negative 1. 10i plus 3i is 13i. In my denominator, the 2i and the negative 2i cancel. The negative 2i squared, remember that I squared is negative 1 times a negative 2 is 2. So 2 plus 1 is 3. And there's my answer. Now I can simplify this by breaking it over the sum, and I can have negative 1/3 plus 13i over 3. Here is my real part. Here is my imaginary part. And realize, look, notice that I have a complex number. Multiplying by the complex conjugate allows me to write it as a complex number instead of as a division problem. Let's try one more of these. Write the quotient 2 minus 7i divided by 1 plus I as a complex number in standard form a plus bi. Remember that I squared equals negative 1. I want to do the same thing. 2 minus 7i divided by 1 plus I. I look at my denominator and I find my complex conjugate. My complex conjugate is 1 minus I. I multiplied top and bottom by the same thing, so I don't actually change my problem. Put parentheses around this to know that I am multiplying. So let's go ahead and multiply. The numerator, 2 times 1 in FOIL is first. Outer, 2 times negative I is negative 2i. Inner, negative 7i times 1 is negative 7i. And last, negative 7i times negative 1 is positive 7i squared. In my denominator, 1 times 1 is 1. 1 times negative, that's an ugly one. The board's off. 1 times 1 is 1. 1 times negative I is negative I. Positive I times 1 is positive I. I times negative I is negative I squared. Let's simplify. In my numerator, I get 2. Negative 2i, negative 7i is negative 9i. 7i squared becomes negative 7. So 2 minus 7 gives this as a negative 5. I simplified in my head so I don't have to have an extra step. Down here, again, my negative I and my positive I cancel. Negative I squared becomes positive 1 because I squared is negative 1. Negative 1 is positive 1. 1 plus 1 is 2. Now I can break it over the subtraction and have negative 5 halves minus 9 halves I, or 9i divided by 2. Either of those are the same number, but there is my final answer as a complex number. We will talk more about this in class. This is a weird and out-of-the-box type of thing. We'll talk about uses of this in the real world, in engineering, in fractals, and a bunch of good stuff in class. But this is the basic idea of adding, subtracting, multiplying, and dividing complex numbers. Have a great weekend. I will see you on Monday.